It's great to be here again, and great to see so many enthusiastic Python people as we're here. So yeah, really thank you as well for rocking down on December. I know we're going down to the holiday season, so really great to see all you all here right now today. And yeah, so we'll just pretty much kick it off. And so yeah, as usual, pretty much we have the Slack QR code over here. So yeah, feel free to pretty much scan it as well, join the Slack community. We have most of our stuff in there. So yeah, feel free to scan it. And if you don't happen to catch this, you can also just catch me later as well and, for an invite too. And yeah, we pretty much talk about everything in the Slack group. So I'd just like to make a quick welcome to country. So I begin today by acknowledging the traditional custodians of the land on which we meet today, and I pay my respects to the elders past and present. I extend that respect to Aboriginal and Torres Strait Islander people here today. So just a quick note on the code of conduct. So our community is dedicated to providing an inclusive environment for everyone, regardless of gender, gender identity and expression, age, sexual orientation, disability, physical appearance, body size, race, ethnicity, religion, or lack thereof. So we have the full code of conduct pretty much here in the GitHub link, but essentially all just boils down to just be nice to others and, you know, like have others be nice to you as well, and yeah, just be respectful to each other. Pretty simple. So on the web, pretty much we have our presence on two main platforms, which are on LinkedIn and Mastodon. So yeah, we have a Melbourne Python user group LinkedIn where we post updates as well each time too. And also we're pretty much starting to inch into Mastodon as well, so you can follow us there too. So what's the agenda looking like today? Well, we actually have quite the packed agenda for today. So yeah, we're pretty much starting it off with some introductions, and I take it that everyone's managed to grab a good drink, grab some pizza, and yeah, pretty much get settled in. So hopefully everyone's been enjoying the food and drinks we've been providing today, courtesy of AWS. And at 6:15, we'll have Daniel talk about, who's pretty much will talk about guide to creating 3D visualizations with Python and the BTK toolkit. After that, we'll have a lightning talk by Liam. We'll be talking about extending Python with Rust, and after that, we'll be having Imron talk about numbers in Python, why you still need to care about low-level details even when working in a high-level language, especially if you work at a bank. And yeah, pretty much after that, we'll just close with some more networking and food, and yeah, close out the doors. And we'd like to give a special thanks to our sponsors, Judo Bank, who's providing us with this beautiful venue that we're all in today, and AWS, who's sponsoring us with the food. But before I go on, I'd just like to hand it over to Lawrence to give us a few welcome notes and also a bit of housekeeping notes.
Yeah, so I'm Lawrence, I'm head of engineering at Judo, so I look after software engineering and cloud infrastructure. For those who don't know much about Judo, we're a reasonably smallish bank, so about 600 people, mainly focused on small and medium-sized businesses, very focused on relationship banking, so very much investing in people, talking to people. So our connection to the Python industry, we're fully Python throughout, so all of our software engineering is in Python. We do some pretty cool stuff here, doing a lot of stuff alongside AWS, so fully serverless bank, so everything's running on Lambdas here, which is pretty cool. So yeah, big thanks to AWS for helping co-sponsor this, and that's basically pizzas and beer, which is awesome. Some basic housekeeping stuff. If everyone could try and keep this place tidy afterwards, and like just put some in bins and throw away bottles and stuff, that'd be awesome. Bathrooms are straight out the other side of the lift. There's probably a fire exit there should something happen. Hopefully not, please. Oh yeah, it's not fun as a 5-year-old here. It's a lot of steps. That's pretty much it from me. Come see some of our engineers, have a chat with what we do here. Most of them wearing Judo Bank t-shirts and stuff. So yeah, that's me.
Thanks so much, Lawrence. And again, just another big thank you again for all the stuff that Judo Bank and AWS has sponsored us with too, as I mentioned before, because yeah, without them, we definitely can't have it this meeting at this beautiful venue with all the food. And also, these are our current organizing team. And I'd just like to quickly give a brief rundown on Programmable. So recently, we're cooperating with Programmable to pretty much do a bit of a shout out as well to them too. So basically, if you're not too familiar with Programmable, it's a Australian software engineering conference, which is happening on March 19. And we have a ticket reserved for, well, it used to be one, but courtesy of AWS, we recently became two lucky members of the Melbourne Meetup. So yeah, pretty much they have a number of technical tracks, including data and talented developer, security, and yeah, pretty much the rest as you can see over there. So if you wanted more information, yeah, come talk to us as well about what Programmable is. But basically, in this meetup, we'll be doing a raffle for 2 lucky members. So pretty much, if we pretty much already provide the QR code, right?
Yeah, there was a QR code at the entrance. If you didn't see it, it's just by the board where all of these certificates or whatever they are. Yeah, just next to that panel. There we go, Sebastian's showing it to us. So just scan the QR code and enter your details, and we'll say who the lucky winner is at the end of the night.
Beautiful. Yep. So yeah, pretty much if you haven't scanned it over there, feel free to scan over to enter the raffle, and you could be one of the 2 lucky winners to enter the raffle to win the ticket for Programmable.
So just on this, Programmable is giving away one of the tickets, but AWS is sponsoring the second one. So thanks, guys.
All right, and for this one, I'll hand it back to Thais.
I'm sure all of you know, but there's heaps of ways that you can get involved with this meetup. If you're interested to do a talk to me, Rinaldi, on LinkedIn tonight, and we can talk about the structure, what we expect. If you want to sponsor, there's always money to be thrown in the game. So yeah, come talk to us as well. And volunteering is a big role for us. We're very thankful for the guys that are here today helping with registrations, Mike showing where the QR code is. So yeah, if you'd like to help moving forward, just talk to us. Oh, thank you. And for the new year, there's nothing really set in stone, but in terms of the structure, we're hoping to continuously have monthly meetups. In terms of the talks, we're going to aim for 2 longer talks, half an hour each, and potentially throw in some lightning talks like we're doing today. So we're pretty flexible depending on what you guys are looking to do in terms of your talks. So just talk to us and we can work around your schedule. We're also planning for a hackathon, but we don't have too many details on that yet. If you are interested and you want to chat to us about it, again, just come forward. This should be it from us. I feel like we've been talking for a long time now, so I just wanted to invite AWS to come introduce themselves. Sorry, I caught you off guard.
Hi everyone, we'll just keep this quick. Yep, my name is Simon Cousins, so I'm a solution architect in financial services with AWS.
Alex Fraser, account executive, looking after some of our financial services customers in Melbourne, including Judo Bank.
Cool. So yeah, we just wanted to give a quick plug to reInvent, which happened last week. So any of you that use AWS are probably already aware. Our big conference was last week in Vegas. A couple of us in the room were lucky enough to go. Big week, lots of announcements. It's typically when a whole bunch of new service announcements and features get released into the wild, and there's a lot of new information made available, and can be a little bit overwhelming. But we do have reInvent recap sessions that we host in the capital cities around Australia. So next week it's on the 14th, I think, 14th at our Melbourne office. So it's a free event. There's drinks, it's networking. We try to get through all of the announcements in about an hour. I think last week we did it in about an hour and a half, and everyone was bored out of their minds because we decided to literally read out everything. There was a lot of refinement this year, and I think we're going to try and just talk on 2 times speed and get through it all. No, just kidding. Just the major announcements. Most importantly, it's a chance to just have a bit of fun in December on us and catch up with industry peers and just basically have a fun night and just to get a wrap up of what happened. But all the sessions and all that kind of stuff are all being made progressively available on YouTube. So YouTube's now being flooded with a whole bunch of content from AWS, breakout sessions and all that kind of stuff. So there's plenty of new and updated topics, new and updated content on there, which hopefully you'll find really interesting if you've got any queries with AWS services and also how other customers are using AWS services to meet their business goals. So if you want, feel free to come up and have a chat. I'll be around for a little while. But yeah, we'd all welcome you to check out the recap event at our Melbourne office in Exhibition Street next week.
Awesome. Thanks all.
Thank you. Have a good night.
Thank you so much, Alex, Simon. So without further ado, we'd like to go on to the next part. Yeah. We'd like to go ahead and invite our first speaker for this evening, Daniel. So yeah, pretty much we're just gonna get set up quickly as well. All right, everyone. So I'm going to give it to Daniel now. So please join me in giving a round of applause to Daniel.
Hello, hi everyone. Thank you. Before I start, actually, I want to say thank you to Juno. This is looks like a really nice place to work with an amazing view. So if while I'm speaking you're all staring out the window, I'll totally understand. And thank you also to AWS. The pizza was really good. And I have in a past life written Lambda functions with Python and totally recommend. So a little bit about me. I'm a contractor at Coles, so my main employer is 460 Degrees. They have a DevOps practice of which I'm a part, but I've spent the last 2.5 years as an engineering manager at Coles. And to be honest, this talk really has nothing to do with my role at Coles. Coles is a great place, but it concerns previous things that I've worked on. I saw a talk from Ken Thompson, and it's one of the best things to watch because he went to this really sophisticated operating system conference, and instead of talking about anything like that, he talks, he's a keynote speaker, he talks all about this jukebox that he developed in front of, as a keynote in front of a big conference, and I thought, if you're going to talk somewhere, just talk about what you find interesting. So you can find the listings for what you can see here at that link. And I'm here in a personal capacity. I don't intend to say anything controversial, but just in case, I don't speak for Coles or 460 or any of those people. So, a little bit about what we're going to cover. What is VTK? So it's a library that lets you visualize usually the results of some sort of either a scientific measurement or a computation or something like that. So I think it helps a little bit to understand what it's intended for and what the problem is that it tries to solve. So it's a library that lets you import data, manipulate it, and then show it usually as a 3D visualization. And then also tools to create applications out of that. These are some examples. So These are not mine, they're from the VTK website. They're, again, in terms of scientific visualizations, you have a scan of someone's head, MRI images. You want to create a tool where you can look at that data, visualize it, and make some sort of scientific conclusion out of it, I guess. So it's written in C++. It does have an API that you can use from Python, JavaScript, and other languages. And what sort of motivated this was previous work as a postgraduate student where I had my own numerical simulations that I wanted to use to visualize, to sort of do something with the results. And VTK, I think, is probably the right tool for that sort of thing, but it was, and it could just be me that there's something wrong with me, but I found that the learning curve was just too high. And so I think that although it's a really good tool, and it's one of those things where once you learn how to use it, it's really straightforward, but there is a certain bit of theory that goes behind it. And so I'm hoping that by the end of this, you'll learn enough that you can go off, start making your own visualizations. And if you can't use every part of the toolkit, you'll at least have the theory to go on and make your own software out of it. So again, it's supported by a private company, but it's an open source project. More info at that website. So you access it from Python. So it's not a native Python application. We'll go through some of the examples where the API is a bit awkward as a result, but it does have a Python API. And it's still, again, once you learn how to use it, it's quite useful and quite straightforward to learn a little bit more and make more interesting tools out of it. So again, the reason why the tool exists and why, for example, you wouldn't start with Matplotlib or something like that is that when you're working in a scientific field or research field, you're often dealing with something in the real world where you've got either a physical experiment where you're taking measurements, a simulation where you're simulating something in the real world, and you have data at every point on that object. So if you have a heat experiment, you'll have a temperature at every point on your object, or a vector on every point of your object. And so it's not as straightforward as putting something into Matplotlib to make useful visualizations. And again, this is sort of what motivated this. If you look at these examples, so these came out of my my research project. You have two slightly different geometries where what I was trying to do was to write algorithms that would design structures that were mechanically well optimized for particular criteria, but to do that through algorithms rather than learning mechanical engineering and learning structural engineering. And so again, this is another example of that type of problem. You have a 3D mesh. At each point in that mesh, you have some sort of a value that that you would use to optimize the geometry, but you want to display that on this 3D object. So again, what we're going to cover, how you take your geometry, how you plot the values on that geometry, how you might manipulate it using VTK, and then just an example of where all these things come together. So again, it's really straightforward to install. One line with pip to install, and then one line to import the library, and you access the library through the VTK module. So this is a little part of the theory. So you have a visualization pipeline. You start at your source data. You can see on the example there, you basically follow your arrows until you get to your result. Now there's sort of two parts to this. I'm not sure this is necessarily an official thing written anywhere, but it was just my experience using this, where you have your visualization stages where you take your data, you're manipulating it, you create an actor, which is an instance of your object inside your visualization, and then you have your rendering stages where you create an actual renderer and a window and something that you can see on the screen. So again, there's a little bit of a process. Each one of these steps is something that you have to get through, and then at the end of that you have your visualization. Or alternatively, you can just use your filters and manipulate your 3D data that way without necessarily looking at it. So we're going to go through, this is a simple sort of hello world example, a cone that you can see on a window and the steps to get here. So again, you'll create your source geometry. In this case, you've got your cone. You can see the first line there. Now, the steps, the mapper steps, the best way to describe them is if you have a series of transformations, you'll do that in the filter steps, and then the mapper steps will take geometry and join all the pieces of information together to give you an actor, and the actor is the thing that you manipulate in your window. So this is a really common idiom where each step of this visualization is connected by getting the input connection for a mapper, which is the next stage along, and then connecting that with the output port of the preceding step. So if you're comfortable with this line here, you can see how each of these steps connect to each other and how you end up with your final visualization. So again, in this case, the source of the geometry comes from the toolkit. It's something that VTK comes with simple primitives so that you can display simple shapes like arrows, cones, things like that. Your mapper, there are no filters used here. Your mapper takes all these pieces of data and puts them together. And then finally, you create an actor by specifying the mapper that came before. And the actor is really what you can think of as the last step where you've got your object. And then in the final steps, you're displaying them in the window. So again, you have your steps here to create a window. You create a renderer and attach that to the window, and attach the actor to your renderer. So there are a few steps here, but that's it. Once you can get through here, you've basically got a hello world example, and you can keep repeating that for any type of geometry that you have, or any type of new thing that you want to display using VTK. So I have a simple pre-recorded example. So in order to not tempt the speaking gods, I've pre-recorded these, and so basically you have, as you can see here, a nice simple cone, which is nice. You've created a 3D model of something, but I think it's not quite I think, really that interesting, and it's certainly not a complete application. So we go from here. All right. So what you might be more interested in is, rather than simple cones, how do you take a complicated 3D model and bring that into VTK? So there are, for certain file formats, there are people who've already written readers for like STL files and things like that. But you can also define your own mesh. So I think that, once you get through one of these examples, you can then go and use the pre-existing readers, which would probably make the task easier. But VTK has this idea of defining different types of meshes with different levels of generality. So if you look at the first mesh, it's an image format. It doesn't necessarily need to be a picture, but it's something where your geometry is very regular, the distance between your points and your readings is fixed, and so you don't necessarily need to define the entire geometry. You might just define the overall size of the image, and so you might use this if you have probes on a particular device where all of your probes are at a fixed node distance. Again, a rectilinear grid where the distance between your nodes is not necessarily fixed, but it's regular. So in that case, what you can do is you only need to specify the distance between your points in one particular direction. And again, as you can see, as the mesh gets more and more irregular, you have to specify more and more information to completely define your geometry. And so what you would do in a real application is you would find which one sort of makes sense for me, and you would pick that. Now, what we're going to try to do is define a complete mesh. So, do I have a... All right, so a mesh is a collection of cells, of points, and the actual data on that mesh. So these things are supported by native C++ data structures, so they're not necessarily using arrays, but if you think of these as these are C++ data structures. They're not lists from Python, but they're supported through the API. So if you think of your cells, each cell is an array-like data structure that has information for your cell. And then the cell, in this case, is going to be a triangle or some sort of similar geometry. And then the triangle itself is just a mapping between the nodes in that specific triangle and the points defined in this other data structure here. So we'll look at this example here of a single triangular element. Now what we've got here is this point here is numbered 0, 1, 2. So that's the number on the left. There's a value, so a piece of data at this point here, 0, 1, and 0.5. And then the cell itself has a piece of data. So if you think of what this might be from a numerical simulation, depending on which software you use, you might have a single scalar value at each point or a single scalar value for the cell. And you might want to show that in some sort of visualization. So again, you create each of these things from the VTK module. You have your points, your cells, and we're going to create two meshes and a single triangle. So again, this sort of points to how the API is a little bit awkward. You have to define the geometry for your point. In this case, it's a 2D model, so the X, Y, Z positions all need to be specified, and the Z position is 0 because it's a 2D model. And you can either specify it like this, or alternatively set the number of points. And this kind of points to how this is, again, not a nice sort of idiomatic Python library, but you can see the C++ underneath sort of showing itself. You have to allocate the size of your collection before you start putting items in. And again, you take that mesh and you set the points and you set the cells that constitute this mesh. In this case, 3 points, 1 cell. And you're also specifying the data. So the way that you specify data is in an array. You set the number of components. So the number of components is whether it's a scalar value, in which case it has 1 component, or a vector. And I mean in the mathematical sense of a vector, it would have 3 components. And then you insert that data into your double array. So in this case, just 1 piece of data for the cell, and you set that to the mesh. So we've got 2 meshes. The mesh will get the cell data, and then you would presumably also specify the point data, which we skip, but you specify it in just the same way, and you assign that to the mesh. And the rest of the rendering steps are just as we saw before for the code. So again, it points to this idea of once you can get the code, once you can get this next example, you've now got enough information to put a small mesh onto a screen. So in this case, there was a single value for the mesh, for the cell rather, so it was a single color, and here you have 3 nodes with separate colors, and VTK is a nice little blend of those colors together. So this sort of, again, points to this thing that you're trying to do when you're working on scientific or engineering problems in the real world. You have a real piece of geometry, and you try to display your data on the surface of that geometry. So All right, now a slightly more complicated example, 4 elements, 5 nodes, again, different pieces of data for the nodes versus the elements. You have, in order to define specific colors, and that's an important part where you need to create colors that meaningfully map to the data that you're trying to represent, you create these things called lookup tables. So a lookup table is basically a mapping between the value at that point and the color that the application is going to choose to show. So there are a few different steps, but basically if you get through each of the 5 steps on the points there, you've got a lookup table. So obviously you want to create one. You set the range of colors, so whether you want monochrome colors, rainbow colors, depending on what you're trying to achieve, you map between those colors and the values themselves, which we do here. So again, you can do that you can do that in a couple of ways. One way you can do that is by creating this thing called a color transfer function, where you basically specify the color at certain points, and then it will give you all the intermediate colors. So it's a little bit awkward that you create this transfer function, you specify a color. So the first value is a numerical value, and the next 3 values are your RGB values. And then from this thing here, you then populate all of the values in the lookup table. So again, it's not quite as elegant as you would like, but if you go through these steps, you then have a lookup table, and you can map between the colors and your results. And of course, as I was saying before, the mapper collects all the different parts of your model. So the geometry, the lookup table, which is how the colors are assigned to the geometry, and then that would be fed into an actor. And this is from one of the examples we're about to see. You can also annotate the legend with separate colors. So here you've got 4 different ways of rendering the colors, where you can see these values. If you look at the legends, they correspond to the values of the nodes of the cells. And depending on the different rules that you set, you can create your own color visualizations. So again, you can also, if you wanted to create categorical data, that was the purpose of that previous step. And I think one of the last steps is about transformations. I think the code is relatively straightforward, but once you've created your model, you've created your actor, you have to actually position it somewhere. So you can either rotate it, put it in a specific location, and you can scale it depending on if you want to scale it by a fixed number, or depending on what sort of complicated scaling you want to do. So I think there's sort of a bit there, but we have everything now that we can basically create a reasonably complicated visualization. And so I know that it may have gone quickly, but you've basically learned everything that you can in order to start making things like this. So this isn't the result of a numerical experiment. These are just equations in 3D equations. But again, you've got your 3D surface. The height corresponds to a particular color. And all you need to do for the specific example is specify the equation that you want, and it will plot it in 3D space. So the way you get there is there's quite a bit here, but basically all that this is you're counting out the numbers for the nodes and elements, and then you're assigning a value for each node and element based on how you counted them before. There's a little bit of complexity to that, but that's not really necessary for any of your applications unless you're making a 3D plotting application just like this. Other than that, everything that we've learned before you can do to create something like this. I think the only exception is this little outline filter, which is, again, going back to the pipeline filter step where you just specify your geometry and we'll give it a nice little outline like this. So I think I've got an example of this as well. So again, all you need to do is with this little specific example, you provide your equation, it'll plot it in 3D space, and you can move it around and you can visualize it. So you can see just as easily if you didn't have like a maths equation, if you had, let's say, an MRI or something like that, you would have a similar model defined by the results of your MRI scan instead of a specific equation, and you would be able to again display a scalar field on your MRI results if you wanted to do that. Example, and now any questions about what you've just seen or anything else?
Here, I'll bring over the microphone for you. Yes, we've got here. Could you convert your main mesh into an STL file once you've created like points in that?
If I recall, I think for STL specifically, there are output, what would you call it? There are writers for STL files, but you would also just as easily maybe want to import an STL file because that's what you're actually visualizing. But yeah, so that's pretty straightforward. And this example was maybe more complicated than it needed to be, but because you saw there's different types of geometries. This is the most complicated, but I felt if you go through this example, then the other ones are maybe easier. And if anyone's interested, I linked the GitHub page, so if you want to go through these examples yourselves. But it's not any more complicated than what you've just seen. Ned?
Thanks for the talk. It was really good. Nice overview of the library. Around the high-level interface, particularly what you showed at the start, so I got two related questions. The first one is, how intuitive did you find it, or do you find it when using it, like sort of modeling these things? And then a more concrete version of that is, I think I was a bit thrown by having it start with the source data. Like I would have thought, hey, create a thing that you then put the data in, like it's sort of connecting to this. And does that mean like if you needed to create multiple cones, would you have like a composite sort of object with multiple cones?
All right, I can only remember one thing at a time. So I'll start with, remember I'm learning all of this from scratch, how everything works. I would say that I feel if you play video games, it's probably about as difficult as that to maneuver around. It is tricky, so what you might want to do if you're creating an application is make it possible to click on things, show values, specific values at that point, do more complicated types of analysis. The way you would do that is that there are types of filters for all of these sorts of things. There are types of interactors. So having covered interactors is there are different types of interactors that will take like a mouse input, keyboard input, and have some sort of a behavior out of that. So these all work in a different way, but the way that they work is, as you saw here, where you create an object, you connect it to the pipeline using the same syntax as here. So the difficult part really is just maybe trawling the documentation and finding what exactly you want. I hope that was enough question. Enough answer to the question.
Yeah, that's great. And if like just in the specific example of the cone, like if you had a whole series of them, would you create some sort of composite object that is the source?
The example you saw here was a scalar field. A scalar field is a single number at each point. If you remember back, how many people deal with vectors when they're into maths, but you have a vector is something that has 3 values and usually like a magnitude and a direction. So again, there's ways of doing that in a straightforward way using this library. Alternatively, you could create an arrow at each point and define a transformation for the size and the direction. But for these sorts of things, because a vector field is a common thing from science, there are, for a lot of those types of operations, there's like already built-in ways to do them. So I can't think of the name of the filter off the top of my head, but you would have to find either references or examples. And that was part of the difficulty with my learning how this works, was that a lot of the references were in C++. There are Python examples, but there isn't a nice hold your hands, start from scratch kind of set of examples. So that's me talking a lot. At some point I answered the question.
Sorry everyone, that's pretty much going to be all the time we have for this time around, but yeah, if you do have any questions, feel free to have a chat with Daniel during our break time later on, or at the end of our meetup as well, and yeah, I'm sure Daniel will be sticking around as well.
I'll be around if you have more questions, come say hi.
Beautiful, thank you. Let's give everyone. And so now we'll be having Liam deliver his lightning talk on extending Python with Rust.
Yeah.
Beautiful. And again, let's give Liam a round of applause, everyone.
Can everyone hear me okay if I don't use the microphone? Like at the back specifically, is this alright? Yeah, we're good. Okay, how do I microphone? Put that down. G'day, I'm Liam. Nice to see you all. Hope you're having a good afternoon. I did not manage to be a lightning talk. I knew it was. I didn't know that at all. So I will try and stay on the limit days wherever you are. Sorry if I don't. We're talking about extending Python with Rust. I'm hoping that you leave this with somewhat of an appreciation for how complicated it can be, but actually how achievable it is to use multiple languages at the same time. It's an interesting piece built on years and years of stuff like the Linux kernel and all the other bit of operating system software that are out there. But it is possible to build increase in Python, to make it a lot faster and do it less time. So I hope this is somewhat useful for everyone. What are we trying to do? We're writing code in Rust or C or C++ or really any language. There's no limitations there necessarily. There is one caveat that I'll cover later. And we want to call Python, so this is Python. We still want to use Python. Obviously, we want the main benefits, right? So we don't want to get rid of those, but we do want to extend it somewhat. It's the main Python. So, don't pay attention too much to this diagram. I know it looks confusing. You've never seen one of these before. Don't stress, it's not going to be a test on this later. I just wanted to highlight that we have this kind of application level API that is almost all used, right? I'll go into this a little bit further. But under that, you have a thing called the API, which is the application binary interface. And I'm guessing most people haven't heard of it. I certainly haven't. And I studied this stuff. I went to the University of Electrical Engineering and studied operating systems. So we didn't even cover that. So it does get kind of detailed at some point. We mostly cover this hardware. But that's kind of where it fits roughly in the stack. This diagram is correct. But it's essentially an interface between two compiled binaries. Which if you've ever used a dynamic library before, you've written everything in C or C++ and you link, and you've had the hell that is into libraries and dynamic libraries and God knows what else. You've already used the API before. So that's exactly what it's doing. Under the hood, C is communicating with whatever your application is. It allows for low level and faster execution, and there's no safe C competitor. This is the thing that I just mentioned, but almost all the kernels that we use in operating systems are written in C. So far, as in 2023, no competitor has formed to the API for C. So technically, the application binding interface is cross-language, any language you can use it, but everyone sticks to the C standard, specifically the C99 standard. That sucks. It hasn't been improved so far. It's probably not going to improve anytime in the near future. But it is worth noting, if you can't do it in C, you're not going to be able to do it in any other language. And it's very interesting to know. Let's talk about APIs versus APIs real quickly. APIs, will have abstractions, types, functions, variables, you're writing in code. Most of the time you're doing source code communication, so if you're writing a Python library, you would have all seen, you can actually go into those libraries, read the code in Python that the library is using. It's a good little hack if you're ever getting an error and it's caused by the library. Whereas the ADI is binary level abstraction. So we're hitting register stack calls directly, and I know what has to do that these days, return values, exceptions, things like that. It's almost all kernel level communication, like syscalls are happening via the API. And I wrote no rules and lots of rules, kind of equal and a little bit cool, but there are essentially no rules with APIs. You can do more or less whatever you want, and people do whatever they want. Everyone's seen APIs on the web, everyone's writing fancy web frameworks, everyone writes their own APIs. People forget that what you're actually doing is executing a function on someone else's computer. That's always what you're doing with an API. Whereas with an API, you have to stick to the rules so that it actually works with an operating system. So it's quite important. This doesn't mean that we can't use it though. This is a super quick example. If you don't know Rust, you don't need to know Rust. The only real important thing is we're doing a really simple sum string function, just adding some strings together. And we're doing some kind of boilerplate code to let it get called from Python. This is using a library kind of sort of within Rust called PYO3. You'll find out more about that in this. This is it from Python. So we're writing Rust code. We can effectively do anything we want. It can be as low level as you want. You can do anything on athletes or touch on all the frameworks. And then we just call it from Python. It's really simple. It's not that complicated, even though I just said that the API is quite complicated. Why would we do this? Main reason is Python is slow sometimes. So if you're looking at stuff like lists of strings, or if you're doing regex, or if you're doing file loading, or any of those really common repetitive tasks, especially when you have to do lots of them, so if you say loading 10,000 CSV files, Python is going to be noticeably slower than any other language or any other compiler language, purely because it has to interpret each file. Dynamic typing is always the best option. So I'm sure everyone who's Python is kind of used to it. I certainly was when I was just using Python. You get very comfortable with not having to worry about what types of variables are. There are a lot of cases in real-world engineering where it matters what types of variables are, especially if you're looking at anything database SQL related. Also any structured data, JSON, YAML. You don't have to do it. I'm sure everyone's used Python to load JSON before. It's a very common use case. You end up with a stack of statements, a stack of all loops, and then as soon as someone changes the JSON standard, it breaks. You get to maintain cross-functional team capability. Lawrence, that was you. You're being judged.
Have a last half as well.
We're hoping not to make that happen.
Thank you. I think
There we go. Awesome. If you're maintaining cross-functional team capability, what I mean by that is if you're a data scientist, for example, that love writing Python and don't want to learn any other language because they're data scientists, you can write the code that those data scientists use, and they can just call it directly from Python, just like that first example. So there's actually almost nothing that you need to change from the Python level to be able to accomplish this. It's quite easy. Here's a really quick example. So running the vanilla Python here, we're just counting pairs of repeated characters within a single string. Super basic, super easy. Vanilla Python, this is microseconds, by the way, the y-axis. I'm not going to talk too much about this. You can see the results. Obviously, the POC implementation is a little bit slower than Rust, which is kind of interesting. That, as far as we can tell, that mostly has to do with modern file optimizations within Rust. And Rust isn't held back by any of that API bullshit that the Linux kernel has to deal with, so it can be a lot faster. Obviously, NumPy within Python the processing library works quite well. Although this is kind of somewhat of an edge case, but it's quite a small example. I've got code and why wouldn't you do it? Hopefully everyone in this room knows the meaning of that first one. Adding a new language, adding a new framework to your stack is complicated and it increases the complexity. We've all had to do with taking the debt. No one wants to. This potentially can do that. The API is not great. Like I said, it's very little documentation on it. The documentation that exists is mostly low-level kernel space, Linux type stuff. If you have to go digging into it, it's probably not worth your time, and I wouldn't recommend using this approach. It has to introduce new language in that environment, so Rust uses cargo, there's some tooling along that. Rust is quite good on that level, but it is still an added complexity in the DevOps process. Your platform is going to hate you. It's not Python, it's a new language. And there is an additional compilation step because we're using the API, the application binary interface. We have to compile it first. There's no way of compiling otherwise. So we do have to compile Rust and for the Python, just for the Python interprets, which is more or less fine. So when should we use this? Like I said earlier, heavy functions from Python, so string parsing, file parsing, any image processing, anything that, like I said, you have to do many, many times, and it can be optimized, and the compiler will almost always do a better job than your Python interpreter. Unfortunately, that's just how it is. Anything complicated, or doing it in inverted commas or important, structured data reading. What I mean by that is, I've got an example on the slide that if you're writing, this is just a pretty standard file in Rust as a main code. If you don't read Rust, sorry, it's not that complicated though. Most of the stuff you can do, the comments you can about to see, these aren't actually comments that go into the struct. But all we're saying here is that we're expanding a hash map from a string to a string. We're saying that there's an option, so either it exists or it doesn't, and that's a vector of strings. This will actually load with just a little bit of boilerplate, a YAML file every single time. If it has the field, it will pull it in. If it doesn't, it uses that option earlier. Once you've read this, you never have to write it again. So if you've ever done the whole dance with Python saying, okay, here's a YAML file, read this, if that's there, then do this, if that's there, then do this, all that somewhat goes away with Rust because you can just explicitly say, this is our YAML file, this is what we're expecting. And if it doesn't hit that, then sorry, not going to load. It will increase the speed of processing if you are routinely doing JSON files, YAML files, even XML, although you should do it XML because it's 2023. So why Rust? It's future-proof. People throw that term around a lot. I put a question mark after it because it's impossible to say what it is and is not future-proof in the world. But for now, Rust is actually future-proof. If you take this exact same code and run it on the first version of the Rust compiler, or the last version that got released yesterday, or the nightly build, it's always going to run. Rust as a foundation really does a great job maintaining compatibility across versions. So there's no like C99 to all C++ shenanigans. It's going to run. If you can get it to compile, and it is somewhat difficult to get it to compile, if you can get it to compile, it's going to run, it's going to compile in a year, it's going to compile in 10 years. It's fast, it's compiled language, it's kind of free. Cross-compilation in Rust is amazing, so you can just set target and compile it for another architecture. At the moment, I'm doing some hobby stuff in WebAssembly, and it's awesome. I can write Rust, it compiles to desktop, it compiles to x86, it compiles to WebAssembly, I can run on my Raspberry Pi, it compiles on ARM, no problems. It's just a simple compiled by. The ecosystem is amazing. If there's any data engineers in the room, Poland is really cool. It's kind of meant to be a drop-in replacement for NumPy or any Python number processing. It's quite good. It's being used a lot in the industry at the moment. It's very fast as well. Serde and Tokyo is the asynchronous library for Rust. Awesome to use. There's a lot of asynchronous programming happening. There's a lot of web services being linked. And Crates.io is kind of like the Node.js or NPM package for Rust. It's also great. I already mentioned the type system earlier, but the type system in Rust really speeds up any sort of database or SQL or really any processing where you know the file types and they have to be correct. So if there's any ambiguity, which Python obviously introduces quite often, it's almost always a good choice. And in my opinion, it's the most productive developer ecosystem. I just feel fastest when I'm writing in Rust. That's not because the language is easier, it's definitely not. But again, once you write something and it compiles, it's almost certainly going to work. So if there are bugs, then what that you are really forced to compile. I already showed you this. This is kind of me. I'll put some links in here, and this QR code will just take you through slides if you want to look at anything. But I put a pretty cool article from you guys at Red Hat on doing this exact thing. And some of the numbers you saw earlier came from a very similar piece of code. The recommended library for doing this is IO3. It's very easy to get started. It will handle all the API work for you. There's just a link to the best way to install Rust, which is just how good. And then there's a Wikipedia article on application finding interface. That's kind of it. I guess in summary, if you want really great performance, and the code has to be correct. You're already using Python, you have multiple pages of Python. Extending it this way using the API is a really efficient way of doing things. It really allows you to just take whatever the slowest function is one at a time and do that. And it's really powerful how this will work. I hope you got something out of this. Thank you very much. Any questions? Yeah.
I mean, I guess my question really is kind of why. So if I'm a Python programmer and I'm trying to do fast stuff, at the moment I'm mostly using C libraries anyway. Like I'm using NumPy, I'm using TensorFlow, I'm using whatever. None of those things are actually Python, right? They're just a veneer. They're a nice veneer, don't get me wrong, unlike the VTK veneer, which is frankly awful. I agree with the speaker, it's a terrible one. But the other ones, they're great. Why should I switch to Rust when I'm already using a whole bunch of native libraries? And if I'm switching to Rust, why am I adding yet a third language to my compilation stack? Shouldn't I just switch? Like if Rust is better, cool, maybe I should switch my whole team to Rust.
Yes.
But what's the point? And that's obviously the right answer. You know, I agree with you. That's obviously the right answer.
Like I said, that is definitely the right answer. I did mention that you can actually use the API fully through C++. C. You can actually use it through Java as well.
Which is main man. Like it's main man in the parsing command.
And that is kind of why I think that Rust is probably the best choice if you are going to go down this route. Simply because of static typing, simply because of the reason that Rust can actually self-compile. It's the only language apart from C that can self-compile properly that doesn't use any shared C libraries. So if you look this up, almost every programming language is ever used is ultimately called C, right? Like most people have an appreciation of that. Even on a library level, there's no compilers that will actually compile straight down any C libraries whatsoever. That's not really a great reason. If you're already using C and C++ and you're breaking your stack, then you can use exactly the same methodology. There are ways to do it. You'll hate it. I guarantee you'll hate it. Just because Rust doesn't make it easy, and simply because of the type system. Like the problem you mentioned, right? One of the largest problems with the API is that you have to be very precise with what the variables you call. You can really break that compatibility. So Rust is great for that. But yeah, you're right. Like, if you're using C and C++, you're not going to get much of a performance boost. But you can do exactly what I said to you for C and C++ and Java and technically any other language. It's just that Rust makes it really nice to work with the API. Anyone else? Yeah.
So isn't that be quicker? It's because that it's built on Rust, essentially.
Yeah, I mean, polls and
like as opposed to pandas. So
I mean, there's a lot of Google polls versus pandas comparisons. I think at the moment pandas probably beats it out and it's faster. By the way, pandas is like also using the API. It's just under the hood, right? So pandas is mostly written C++, C, and it's using this API under the hood. I think the low stuff polls is making a lot of ground, especially with the SQL and ORM building, and the way that they've just really used the Apache to set build integrations from the Java perspective. But we'll see what happens. I mean, I use pandas every day at work. So like pandas is still fucking awesome, like don't get me wrong. But we'll see what happens. I think the polls has a long way to go so far.
has lazy evaluation.
It does, yeah. And also like I've been using some of our inbuilt where I write a lot of SQL work at the moment. And you can write SQL in Rust, which is pilot to SQL, which sounds kind of crazy, but it means that if there's a problem, I can just fix it in Rust in 2 seconds and recompile it and everyone's happy. So yeah, it's one to keep an eye on. I wouldn't probably switch as a replacement just yet. Anyone else? Cool. Well, thanks very much. I hope you got something.
Okay. Thank you. We're going to take a very quick. All right, I'm just going to pass it over to Imron now, who's going to finish up the night. So enjoy.
Thank you. So my name is Imron Alston and I'm the principal engineer here at JDaniel. And today I'm going to be talking about numbers in Python. It seems like a bit of a basic topic. Last month we had talk on, the state of AI and machine learning.
we had talk on the GIL, Global Interpreter Lock, and the impact that's going to have on the Python community, sort of very big, really impactful topics. And I'm talking about numbers in Python. So there's actually a reason for that. So why this topic? I really want to encourage everyone here in the community to feel free and welcome to come up and give talks. And you don't need to be talking about a world-changing technology. You don't need to be talking about some super impactful technology. It's as Daniel said, speak to what you know, what interests you. Even simple topics still have depth. I learned some things when I was preparing this presentation that I didn't know. I ran it past my manager, the talk, in preparation. He didn't know them either. So there may be some surprises in here for even experienced developers. It's also based on a true story. This came through as a PR when I was trying to think, oh, what can I do for my talk? And the PR came on my desk, and it's like, oh, okay, that's an issue. And there was a learning moment, a teaching moment that I could give to the developer who wrote that code. And that's really what you can use to create a talk that's going to be interesting. It's a learning moment. You might think that in a room of 60 or 80 people, there's a whole bunch of people who know everything, and maybe there are 40 know-it-alls in the room. That still leaves 40 people who don't know it all, and maybe will learn something. So if you were debugging something for a week, a production issue, and you finally found it, that'd be a really interesting talk. What broke? How did it break? How do you fix it? It can be anything, and anyone can give a talk. So today it's me as principal engineer, and we've had experts talking about other things, machine learning and so on, but you don't have to be a principal engineer or a senior engineer. You just have to be someone who has some topic which might be interesting to the Python community. So I really encourage you to have a think about what you can do, because this user group is only going to be as good as we make it. If we limit all of our talks to world-changing technology, very soon we're going to run out of topics. And so think about what you can do. And I have somewhat of a vested interest in asking for this, because if you don't come up with talks, my manager will be, hey, we're sponsors of the Python Meetup. You're a principal engineer. You should give a talk. And that's not quite how this talk happened, but it's, I'm sure if we run out of topics, that's where things will start to go. You'll hear a lot more. This will become the judo technology talks. So, I'm going to begin. So the subtitle for this is, you still need to care about low-level details, even when working in a high-level language, because sometimes there are things that trip you up. So I'm going to just give a background about approaches to complexity of different languages. So we'll start with C++, which is notorious for its complexity. And it really says, developing software is a complex and challenging task, and you need to know every single detail. And if you don't get the details right, it's going to crash at runtime. On the other side, you have tools like Rust. It also says software development is a complex task, requiring knowledge of a lot of details. And if you don't understand all of those details, it's not even going to let you compile. So you'll be stuck on the compile, you'll be bashing your head, and you'll be stuck there. And then finally, you have Python, and its approach to complexity is software development. It's complex, it's challenging, a lot of details. But I'm going to extract all of those details away, and you don't really need to care about them, and I'll just take care of all the details. It does so, but it leaves some performance on the side. So there are ways to get around that, as Liam was mentioning. So for most people, you don't really need to care that much about performance. Even Python, it says, you might have a machine with 24 cores. I'm only going to let you use one of them. And it's still enough. So we'll start with, again, low-level details, numbers, how other languages deal with them. In C++, and I know if there are C++ people here, you'll be telling me that's not modern C++. I know. It's just, this helps illustrate my case. What you're doing is you're taking a number, 65,535, printing it to the screen, adding 1, printing that value to the screen. Any guesses what the output for this will be? We've got a 0. Undefined. So the first one, it'll print out that statement there. Is that you add 1 to it and it prints 0. So not expected. Why is that? Because in C++, an unsigned short int is 16 bits. And the maximum number of that you can hold in 16 bits is 65,535. If you go over that, it wraps around to 0, and here you have 0. You can get around that by using a slightly larger data type. So move the data type now to an unsigned int, which holds 32 bits. Any ideas what this output's gonna give? Got a couple of zeros. Anything else? -1 and 0. Where does the -1 come from? You can see in C++ you need to mention what kind of type you are writing. D is for signed ints. So we are printing a signed integer, and this is an unsigned integer, and I don't know if you know signed versus unsigned, but half of the address space goes to negative numbers. And if you go over the maximum signed digit, it wraps around to -1, which is what we've done. If you want to fix that, you actually need to specify when you're printing, hey, I'm actually an unsigned value. And now when you print, you get what you would expect. Also 0, you know, prints the first one, you overflow it, it goes back to 0. That's okay. C++ has even larger data types. If you run out of 32 bits, you can switch to something with 64 bits. Anyone want to guess what the output for this is going to be? Everyone's already given up. So, again, we've got 64 bits. We're only showing 32 bits. What's going on there? Again, it comes down to this. You're now printing an unsigned, but you're printing a long. What you need to do is stick a long in front of it to say, I'm printing a long. And now it will print a long, and if you overflow it or wrap around, it also go to 0. This is not particularly great. There have been cases, most notably, I don't know if anyone knows of the Ariane 5 rocket. I see sneakers up the back. So it was a rocket developed by the European Space Agency. They had, the rocket was taking off. In their software, they had a 64-bit number. They squashed it into a 16-bit number, and the rocket said, oh, I'm getting weird data from my sensors. I better veer drastically to the left. And they veered drastic to the left, and they decided they better explode it. And that's what happened. So you need to pay attention to the details. If you don't pay attention to the details in C++, your programs will crash, maybe even explode if that's the domain that you're working with. Ints in Python. Anybody know what precision or how many bits Python gives you in an int? Pretty much, yes. So in Python, I say integers have unlimited precision. You can go as high as you like, and I don't care, it completely abstracts the underlying machine away from you. You can have as much as you want, limited only by your memory on your computer. So basically the same sort of program, equivalent of the C++ that we just saw. We have a short value here, 65535, the same int value, the same long value. The long value multiplied by itself to be a super long value. And if we print it, we get what we expect. 65,535 plus 1, 65,536. It's an int. Do the same with the maximum 64-bit value, plus 1. You get maximum 64 bits plus 1. It's an int. Same again, with an even bigger value, and even bigger values. Unlimited precision, that seems pretty big. How big can it go? Let's try and figure it out. So here's a Python program. That random int all it does is it generates a number between 1 and 9, not 0, because if the first digit starts with 0, Python won't parse it. And it basically spits them out, prints as a Python program. So what it's printing there is valid Python code, generates a random int that is 1,000 digits long, and it multiplies it by an int which is 1,000 digit long, and you can run it in Python. And it works. I haven't tested that the number's correct, but I trust Python that it's kind of good. But even 1,000 is quite a bit of number of digits, but it's not a huge amount. We can go even higher. And we can put 1,000,000 digits. Number with 1,000,000 digits multiplied by a number with 1,000,000 digits. Do you think it's going to work? No. So what Python has is you've got unlimited digits, but it also sets a sensible default that's like, you know, if you're really trying to parse that, you probably might be doing something wrong and you might want to think of different ways to do it. But it says if you really want to do it, you can bypass this limit and see where it goes. So I did. And you can either set it in your program, but because the program itself has these large numbers, you need to set this outside of the program. I also didn't want to print the output to the screen because it's going to be a lot of output. So I wrote it to a file, and I thought, just for interest, I will time how long it takes. It kept going and going and going. You can see there it's been going for nearly 42 seconds, using 99% of its one core, thanks to the global interpreter lock, running away. And it eventually completed in just over 90 seconds or so, and it printed out 2 megabytes worth of numbers. Again, I assume it's correct, but it does what it says on the tin, right? Numbers are unlimited. We can have as much as we like. Ints are unlimited. So moving along, then we move to floating point numbers. So these are numbers with decimal places. And that has some implications for not just other languages, but also Python, which we'll see in a minute. So here, you can see we have a program. We've got a double value here, 4.685. We're going to print it. Anyone want to guess what we get? Okay, we get the same thing with a whole bunch of zeros at the end, because by default, C++, when you use printf, will print 6 digits of precision after the decimal place. If you only want 3 digits, you need to manually specify that. If you don't, you won't get them. So that's how you would do that. If now you add an extra digit to the end, and you don't change your code, well, your code will round. So you can see it rounds up, it goes to 3 decimal places, and it rounds, as you would expect, using standard high school maths. And you can do this for different levels of precision as well. So if you wanted to print to 0 decimal places, anyone want to guess what we're going to get? 5, that's good, you've all done high school maths. If we round to 1 decimal place, what are we going to get? What's that? 4.7, correct. 2 decimal places? Great, pretty simple. But again, complexity that we need to be aware of, because if we don't pay attention to these details, then we get in trouble, we don't get what we want. How does it work in Python? So Python, under the hood, also uses doubles because it's a hardware feature. It means they're nice and fast. But it also means we run into many of the same limitations that we get. We don't have infinite numbers that we can use like we did with ints. We are limited to floating point numbers, which in Python boil down to a double when it's running in the Python interpreter. So what we do get in Python though, if we have a number, 4.68, and we print it, Python knows that we wanted 2 decimal places, and it will just print it out. We add a digit, again, it will just print out what we want. It remembers how much we want, and it shows us just the amount of detail that we asked for. If we want to round, there are also features in Python that allow us to do that. So if we're rounding this value to 0 decimal places, what do we get? What was that? 5. If we're rounding to 1 decimal place, what are we getting? 4.7. If we round to 2 decimal places, what are we getting? 4.69. Wrong. You get 4.68. And you might think, oh, I found a bug in Python. It's rounding incorrectly. It doesn't even know high school maths. And you will go to the rounding page on Python in their docs, and it will say, Python has issues rounding numbers. This is working as expected. It is not a bug. We won't fix it. Please stop asking us to. So what's going on? So on machines today, this is from Wikipedia or Python, I forget which one, the python.org. Floats, they comprise of 2 bits. You have a mantissa, and you have an exponent and a mantissa, and it's the amount of decimal places depends on the number that you want. If you have a really large number, you'll get less amount of the space allocated for the decimal places. If you have a really small number, you'll have more of the bits allocated to the decimal places, and only a small amount to the integer numbers. So that leads to some surprising implications. So we can see that, first of all, we know even though that a double is 64 bits, we only get 53 bits to start playing with for numbers. Okay, and if we start to go over that, we can start to see some interesting behaviour. So 2 to the power of 53, that is now over the amount of bits that we have allocated to whole numbers. You can see that's the number that we get if we convert it to a float. We take that number, we add 1 to it. What do you think the answer is going to be?
Same number.
Correct. Exactly the same number. It hasn't changed at all because that level of detail no longer exists. Once you get over that level, all of a sudden, and the bigger number you go, the less amount of detail you get at the lower end. And you can loop a million times, adding 1. What do you think the number is going to be? The exact same number, which can be surprising if you're working with large numbers. Luckily, most people don't work with such large numbers. But then you can do something like d plus equals 2. What do you think we're going to get? No, we're going to get that number plus 2, because 2 is, that's the level of details. Once we get to that number, we've only got 2's to work with. If we were to go up to 2 to the power of 54, 2 to the power of 56, that range would get bigger and bigger. So you might be skipping tens, might be skipping hundreds, might be skipping thousands. And that's the way floating point works. As you go up in numbers, then you start to lose precision at the end. Okay, so but how does that affect us? Because we're not using a really big number. It was like 4.685. What's going on with that? So and it starts to look as well, because it also affects the smaller numbers. So here we have, we're printing 0.1. And you think, okay, 0.1, what is that? And Python really tries to help us here by sort of saying, well, you put 0.1, so I know it's 0.1, it's 0.1. You say, well, give me a few more digits. What is it really? And Python says, no, really, it's 0.1. And I see someone playing along in a REPL, are you? So you say, okay, well, give me 10 decimal places. And Python's really going to say, no, yep, it's really that number. So come on, give me 20 decimal places. And now you can see, it's like, well, okay, it's not really that number. It's actually this number with a few tiny little bits on the end because we don't have that precision. But still, our number was up here. Why is this affecting us when we've only got 2 decimal places? So you look at this, and same thing we say to Python, give us 5 decimal places. Yeah, you're good. 4.685. Give me 10. Yeah, you're good. 4.685. Give me 20. 4.684. So sometimes the amount will go up, sometimes it will go down. And if you do your high school maths on this, 4.684, and you round it to 2 decimal places, you get 4.68, which is why we got what we saw. How do you fix it? Because if you're working for a bank, you don't want to be making those kind of mistakes. People like banks to be mathematically correct. It's no good if as a bank we say, oh yeah, we accidentally rounded your things wrong, but the Python page says it's expected and they're not going to fix it. Doesn't go down well with customers. It doesn't go down well with regulators. APRA would not take too kindly to that. They want you to be mathematically correct, not technically correct. As well?
If you round in my favour, I'll be okay.
So this is the interesting thing. This is why you need to pay attention to the details. How should a bank round? These are talks we've had recently at Judo. The talks went all the way up to the board. Chief Financial Officer, Chief Legal Officers. It was a board level discussion that was well above my pay grade that I was not a part of. But it is, there's small details that have profound implications all throughout your business. So you need to know these details because, you never know when you can work in a high level language, but you need to know how things are actually running on the machine if you want to be able to engineer reliable software. So, how do we fix this problem? Luckily, Python also provides a decimal type. It does fast, correctly rounded decimal floating point arithmetic. Decimal numbers can be represented exactly. So 0.1 is actually 0.1, not 0.10000000555. Designed to support unexact unrounded decimal arithmetic, rounded floating point arithmetic, and it also is designed to provide arithmetic that works the same way as the arithmetic that people learn at school. This is all from the Python documentation on floating points, so you can go and have a look at it. And it's they go into a whole lot of detail about why there are pitfalls with floating points. Okay, so let's try to fix it. We import decimal from decimal. We create a new decimal type, 4.685. It's a decimal. Round it to 0 decimal places. What do we get? 5. We get 5. As expected. We round it to 1 decimal place. What do we get? 4.7. We round it to 2 decimal places. What do we get? 4.68. What? What's going on? Come on, Python. And if we print it to 20 decimal places, we see we're still getting 4.684999999. And that's because we are literally, it's garbage in, garbage out. We are passing a float into the decimal. And though it looked to us like 4.685 on the machine, this is still 4.684999999 and so on. And so we pass that to decimal, and decimal says, great, I will create a decimal of that value for you. You need to pass it in as a string. So you can pass in as long as you want as a string and it will get it. And that's all right, but in your applications, you're probably not passing string literals everywhere in your application, right? No code exists in isolation. So, and then this is similar to the function that came across in code review. It looks something like this. Calculate value was calculate something else. You had 2 numbers, both floats. You can see the programmer was using Python type hints because the principal engineer at Judo said we will use strict typing in all of our Python code because otherwise we're going to have unfound, we're going to have so many problems in production that we're not going to be able to fix. So we use type hinting extensively. It was multiplying float by a float. It was rounding the result to 2 decimal places. Not good. So this was the learning moment. I wrote a reply in the PR why you don't use floating points and why we should be using decimals. But it's like, well, okay, we're passing in floats. We know if we're going to use decimals, we need to be using strings. We don't want to turn our function into something like this. This is not very good when you are dealing with maths. And now, instead of mathematical numbers, you're passing strings around everywhere. It'll work, you'll get the correct amount, but it doesn't really lead to good maintainable software. So what you really want is to be passing decimals in. And it's like, okay, we pass decimals into this function. where did these decimals come from? So, okay, well, let's walk up the stack. And so we have our function calculate value, which has a decimal, and maybe it's called by a function perform calculation, and gets some decimal from somewhere, passes it in. What's calling perform calculation? Well, maybe you have another function, process rate, which calls perform calculation, which calls calculate value, which is where the decimals get passed down to. And you can go up and up your chain, up and up your call stack, and eventually you'll probably get to a function like this. You are writing a web application, you've got some data that's come in over an API, you get a request body, which is a JSON string, and you load it into the body, and you pass that information into process rate. Well, it's okay, well, what are the values that we get from our JSON string? And we can try that out. So we can simulate that. Have a body, we have an amount, we have a rate. We're passing them in. We load the JSON string from the bytes. And we have floats, which is not what we want because our data was passed as floats in the JSON string. There's a solution to that. Oh, hang on, in a little bit we'll go at the solution. So you can see what happens if we run with that. We can see the numbers that we're getting aren't really those numbers. It's that number, and then a whole bunch of stuff at the end. And when we calculate it, we're now calculating based on this number here. If we round it, we actually get the correct result. But we are accidentally correct. Right? We're not correct on purpose. We're not correct because we've engineered good software. We are correct because this time the digits went in our favor and put us above that number rather than below that number. So when we round in the way that we expect. We are accidentally correct. Accidentally correct is not good enough if you are a bank. So we can go again, attempt 2, same sort of thing. Now we're passing strings into as our JSON. We pass the strings in, we get the strings out, we pass it down, and you can see this time we are printing it out. We can print it out to 60 decimal places, which is more places than can be held in a float or a double, and we get the right answer, 9.88. And this time we've engineered it to be correct. We've gone up and down the stack, and we've engineered it to be what we want. So but now we run into a problem because we're saying we want these numbers as strings. And this is an API that other people are consuming. And how do we get other people to send us strings instead of floating point numbers? I don't know how many people here do web development, but you have an open API contract, and you can say in your contract, you want your type to be string, and you want the format to be decimal. And you want to be careful you don't want your type to be number, because if it's number under the hood, it will still allow number. And you can put in processes in place either at the gateway level or inside your program to actually detect this, and if it's not matching the spec, you can reject the application. And there's a library in Python called Pydantic, which does exactly that. It validates types and data. Like all good modern software libraries, it is written in Rust. And provides a very fast way of basically what Liam was talking about, where you get structured data into a structured array and it's consistent. Pydantic gives us that for Python. It's built on the same libraries. And so what you do, you say, hey, I've got a calculation request. I've got a rate, which is a string, an amount, which is a string. And if you pass in something which is not a string to either of those things, then when you try to turn your request body into a calculation request, you get an exception at runtime. And this is actually a good thing because we don't want bad, I'm getting a time, I'll wrap up quickly. There's still a few more slides. So you get an exception because we don't want bad data coming in. We'd rather be rejecting bad data coming in. Okay, so now we've got decimals up and down the stack. We know we're getting strings here, and we can convert them to decimals. And that's also now going to say, hey, you've got a decimal, we're going to do it, we're going to pass it down. And you pass down strings, and you turn it into a calculation request, and you turn that into a body, and you can see now inside here, we got the parameters that we expected. Okay, so final result. We have converted this to a string. Oh, sorry, we've got a decimal, we're passing in a string. We can see 4.685, it's a decimal. We can print to 20 decimal places. We can print to 100 decimal places. It's what we expect it to be. Rounded to 2 decimal places. What do you think we get? I know at the moment there are 2 schools of thought. There's the one school of thought that says, yes, we have engineered the stack correctly, up and down the bottom, passing strings everywhere, decimals everywhere. This is the final result. We've engineered the correct solution. And there's another people who say, hang on a second, Imron has already given us many, many examples where we don't get the answer I was expecting. It's probably about 50-50 at the moment in the room. So hands up if you think we are going to get 4.68. Hands up if you think we're going to get 4.69. You get 4.68. So really? You're kidding me? So what's going on there? So well, let's try with a few other numbers. So we put in a decimal here, 3.235. We round it to 2 decimal places. What do you think we're going to get? Okay. This time we get the correct answer, 3.24. Yes. Okay, well, how about we round a decimal number? So we go to, we get rid of all the decimal places really. You know, 1.5 is a pretty easy number. What do you think we're going to get? Right, we get 2. And all round happens inside its decimals all the way. So this is actually decimal behavior. This is actually the point where my talk originally ended, and as I was preparing the slides and the screenshots, I ran it and I got behavior that I did not expect. And I was like, that is strange. So this is what I learned when I was preparing this talk. And okay, rounding again, 2.5. What do you think we're going to get? 2. It's like, what? And what you need to realize is that decimals have a rounding method. There are many correct ways to round a number. You can round up, you can round down, you can round floor, you can round half up, you can round half down. Python, as its default for decimals, has something called round half even. You might think, what is round half even? I had no idea what round half even was before I had started preparing this. And what it is, it will round a 0.5 value to the nearest even number. So 4.685, the 8 is an even, so it's going to round towards the even number. Why would it do that? Because it eliminates bias in the numbers. And so it can introduce some errors, but it minimizes bias if you have numbers which are going everywhere. We can fix that in Python. You can simply set the decimal context, and you can set the rounding to round half up. Rounding to 2 decimal places, what do you think we're going to get? This time we get the expected number, but that's not the end of the story. You need to pay attention to details. Details are important when you are working on banking software. So again, here we have, calling it like that, 4.69, correct answer. What if we run it in threads? Right? Python only runs on 1 core, but it still allows you to have multiple threads. And believe it or not, that context is thread local. It will only work in the thread where you set it. So if you set it in this thread, and then you run in that thread, 4.68 again. You can fix it properly by using a context manager called local context. Anywhere you do it, you set the rounding up, and you round decimal, and you get what you expect. Run it inside a thread, you also get what you expect because now this is running in the thread and it's using the thread local context array. You can also fix it properly using quantize, which is a method on decimal, and you can specify a reference number and it will return your decimal with the same number of precision, the same digits of precision as this decimal with a rounding factor that you choose. And if you run it, you can see it behaves correctly. Key takeaways, use decimals everywhere, enforce up and down the stack, use strings to pass numbers, and use rounding context to specify exact rounding. No. That is not the takeaway from this talk. Okay, the takeaway from this talk is if you want to engineer robust, reliable software, you need to care about details. There are trade-offs between speed and accuracy, and you need to know your domain. If you care about accuracy, financial data, GPS coordinates, you don't want to be out by a digit or two. That could be a couple of 100 meters, or it could be a significant sum of money. So in these cases where you care about accuracy, yes, you need to use decimal everywhere, up and down the stack, passing as strings. If you care about performance, use floating point, video games, computer graphics, machine learning. You know, a lot of machine learning is weights and things like that. Runs on GPUs. They have floating points. They deal with them very, very quickly. Weights, you don't really need 64 bits of data. There are training weights that get quantized down to 8 bits, and they still work pretty well. If you want accuracy and performance, use ints everywhere. You might think Imron is a bank, that doesn't make sense. If you've got 0.99%, that's going to round down to 0. And you simply change the model or the domain that you're modeling. So instead of modeling dollars, you model cents. We can model cents 100% accurately in an int until you divide by 2. And then instead of getting 49.5, you get 49. And that's okay, because then you can simply model, instead of cents, millis. So we have 990 millis make up $1. You divide by 2 and you get what you want. And you can keep going up as much as you like. And on modern hardware, there's support even for 128-bit multiplication. So you can have up to 128 bits worth of ints, and you can have millis, and that's more numbers than you will probably need in a bank, unless you live in a country with rampant inflation, which will never happen in Australia. So why this topic? Just to let you know, you don't need to be talking about world-changing technology. Simple topics have depth. I hope you've all learned something today or experienced something you didn't quite realize about Python. It was based on a true story. Judo had talks about this up and down, the levels going right up the board, all the way down to the programmers implementing it. So it has impact on your career and on writing good software. And really, anyone can give a talk. You don't have to be a principal engineer. You could be the principal engineer who gave the code review. You could be the junior engineer who was on the receiving end of a code review. You could be anywhere in the middle. The person, late nights, debugging code, a production issue, anyone can give a talk. Thank you. I know I went a bit over time, but any questions? Yes?
Yeah, great talk. Thank you so much. Great talk. Thank you so much. You provided a bunch of good, I think, examples of like risk mitigation, and maybe falling more into the category of sort of defensive programming and validation with Pydantic. I was wondering if you could potentially talk about other strategies for risk mitigation, maybe around the testing side of things for this world.
Yeah. So I think testing goes so far, and testing is used a lot in Python because it doesn't have types and static typing, and so you really need to have good test coverage, because if you change the field in your dictionary and then you don't catch it everywhere, you might find that 6 months later there was a code path. You had 95% test coverage, and that path which had the changed value was in the 5% that you weren't covered, and you blow up in production. I don't think tests are really enough, to be honest, and this is why you see a lot of the Python world, definitely all the major Python projects moving towards typing, simply because that just gives you so much benefit in terms of stopping problems at development time rather than at runtime. So testing is definitely an important strategy, but simply by using strong typing and being a bit more defensive, you can find most of those errors that you would have found in testing while your actual development, and you can speed things up. So I would strongly recommend everyone use strong typing in their Python, unless you're just writing a throwaway script. But anything which is destined to be, running production, yeah, strong typing.
Yeah, thank you. That was really good. I felt you started and did your talk trying to sell it to us, whereas I arrived eager to find out. It was a really, really good talk, so thank you. I was just wondering, do you know what actually is happening under the hood with the decimal type? Is it doing something like what you showed right at the end, where it's keeping an integer and a separate decimal value and some sort of complicated data structure?
Yeah, it is using some kind of complicated data structure. I don't know the details off the top of my head. There's a Python page on python.org that goes into all of it and how it works. So if you're interested in the details, you can definitely go there and look it up. But it's also based on standards. So there are standards for how these things behave. And under the hood, it is using a data structure. It's not using a double or a floating point type. That's my understanding.
I mean, this shows us really some of the difficulties you get in Python, and to some extent, even the typings don't really help because typings in Python are funsies, compile time toys, not actually representational like they are in other languages, right? Which is kind of what gives you the problem when you parse the JSON. You read in the JSON, you want it to be a decimal. Python knows that it's an integer, and so it will read it as an integer. If you were in another language, the type conversion could be done for you because it would know what you wanted. Is this maybe an argument to move away from Python to something that's actually just more robust, because Python will not?
Yeah. So first of all, I want to just touch on the first point. It's like, the complexity is in software. Software is a really, really complex thing, and you can't escape that complexity. And if you want to be on top of it and write performant, robust software, you need to know those details. You can work in Python, but you still need to be aware of those details. Should you replace Python with something else? Well, there are always trade-offs. So I would love to be writing in Rust, but we don't have really that scope because it's much more difficult to find Rust developers. And also is a lot harder to get started. Rust will beat you over the head. If you get it wrong, it won't let you compile. Your programs will not compile if you don't understand the details and you don't get it wrong. I've seen people give up on Rust because they get sick of that. So Python is more accessible. It's also relatively easy to learn, easy to maintain. You do need to be strict, I think. You need to have processes in place. Anyone who has had Python in production, you've run into none type has no attribute errors all over the place, or places where you've used dicks as classes and you change one of the fields and now it explodes. So you do need to be, I think you need to be strict. There's tooling around that that helps. So there are trade-offs. So we get development momentum that we wouldn't get if we were using Rust. And it's a lot harder to find Rust developers, competent Rust developers who can jump on board and be productive very early, as opposed to Python, where even someone who doesn't know Python can come up to speed with it very quickly. That's definitely the case at Judo. We have a small engineering team. We have hired for people with experience in software development. Some of them had no Python before joining here. My previous Python role before coming here was 7 years ago. I'm predominantly C++ programmer, hence my interest in Rust, because C++ is painful and Rust solves many of its problems. But a lot of good tooling is being written in Rust for Python. I don't know if everyone has used the rough linter. If you use Flake, I strongly recommend checking out rough. It's literally several orders of magnitude faster. What might take 100 seconds might take milliseconds in rough. So there's a lot of really good. Pydantic is another one. You've got a lot of tooling, a lot of libraries coming out which are using Rust under the hood, and that's really the perfect use case that Liam was speaking to. Most of your application can be in this high level, relatively easy to use language, and then in the parts that really need it, you can dip down into something that provides stronger guarantees, stronger safety. So I think that's a fair trade-off to make.
All right, and sorry about that, but with that, we're gonna wrap up the question session for now. But yeah, because we're a bit out of time. But thank you again, Imron, and let's give Imron a round of applause, everyone.
You can ask me a question in a minute.
Yeah, and again, if you want to ask any questions, feel free to grab Imran as well, pretty much at the end of the session too. So pretty much we're at the end of the session, so we're going to get into the fun bit, which is basically a bit of a drawing on the raffle. So I think it's pretty much the what everyone's waiting for. And what we're going to do is we're going to spin the little wheel here, pretty much select 2 times, and pretty much select 2 lucky winners for the Programmable Conference.
Are you cheating? You have to bring it.
That was a trial run to make sure the application worked.
All right, and now we can go ahead with it. So, guys, why did you give it a spin? Let's see who our first winner is. All right, so the first winner is Neil. Is there a Neil here? Oh, beautiful. Congratulations. So after we conclude this, just come up, Neil, and yeah, we'll grab your details, and yeah, we'll give you more instructions on that. And now let's see who our second winner is.
No. Oh, no.
Is this you?
Beautiful. That's it. Oh, beautiful. Hey. Congratulations. Yeah, we'll get your details and beautiful. All right, so those are our 2 lucky winners for this time around. Beautiful. All right, but we're pretty much going to wrap up with that. Yeah, pretty much thank you again all for coming today. It's been really great having you, and yeah, it's been a pleasure. Me and Thais is really happy to see the community that's active, that's thriving, and yeah, just really great to see everyone down here and pretty much for some fun networking. And yeah, pretty much I'll hand it to Thais to say a few words too.
Oh, no, I'm okay. Oh, yeah, no, I did, sorry. Just in terms of registering for the event, obviously you can see that there's not enough room for 200 people here. So just registering allows us to obviously make sure that we have enough food for everyone, but also know that you guys are coming, not coming, whatever. So the meetup.com page is really helpful to know how many people are coming, and it's really important to update the page if you're not coming so that we don't waste money on pizzas like we did last time. So I would really appreciate if you could just make sure that you've registered, and if you're not coming for any given reason, we're going to put a cap on the total number of tickets that we put out. So we'll have a wait list going. If you're not coming, it just basically means someone else gets an opportunity to get a ticket. So that's it. Thanks, everyone.
And just adding one more quick thing as well before we close up. So again, just another call out, as mentioned in the beginning as well, we're always on the lookout for our volunteers, sponsors. So if you pretty much are interested in volunteering in particular, please feel free to come up as well at the end of the session and come to talk to me or Thais, and yeah, we'll talk more about that as well. So again, thank you everyone, and yeah, have a great evening.